Hi guys, David here with another science update. So today I want to talk about this article from phys.org called Researchers Develop New Method for Detecting Superfluid Motion. And I think in order to understand the implications of this, we should take a little bit of time to talk about what superfluid motion is, or superfluidity. And according to Wikipedia, this is a characteristic property of a fluid that has zero viscosity, which therefore flows without loss of any kinetic energy. So viscosity you can think of like the thickness of a fluid. So for instance, if you pour water out of a cup, it has a very different appearance and flow behavior than if you take honey and pour that out of a cup. So that's what viscosity is. It's kind of like the thickness of a fluid. And what it's related to is the amount of friction that fluid has with respect to itself and with other materials. So if something has zero viscosity, it behaves very, very differently. Kind of like the difference between honey and water in terms of thickness, but taken to an extreme. So when stirred, a superfluid forms vortices that continue to rotate indefinitely, which is very unusual behavior. It's not the type of thing that you see with normal material. So this is very much considered to be an exotic property. It's a lot like superconductivity, which is to say that it's something that we know about and we've been able to observe, but it just doesn't happen in our ordinary everyday experience. Back to this paper, we found out that researchers at Rochester Institute of Technology have basically found a new way to measure superfluids. And what's very interesting about this is that one of the main problems with studying superfluids is that all available methods of measuring the superfluid rotation brings the motion to a halt. So these researchers have come up with the idea to pass a laser light through the rotating superfluid, and then the light that comes out the other side picks up some modulation based on the frequency of the superfluid rotation. One of the problems they faced, though, is that the lasers that they were using would also interact with the superfluid motion and interfere with the pattern of the flow, specifically these little vortices. And so if they would measure the vortex, they would essentially disrupt the vortex, which is what they were trying to avoid. But they found that if they picked very specific wavelengths of laser light, they could find wavelengths that would not interfere with the fluid flow. So they claim that their proposed method is the first to ensure minimally destructive measurement. That is to say that their measurement does not interfere with the fluid flow, so they can measure it and have it still stay as it is, and is 1,000 times more sensitive than any available technique. This is a very exciting development, as the combination of optics with atomic superflow promises entirely new possibilities for sensing and information processing. They also showed that the light beam could actively manipulate the supercurrents. So I imagine that they picked wavelengths that would maybe interact a little bit more with the fluid, and then they were able to put currents, specific currents, into the flow based on what they wanted to do. And so now you have the ability to both measure the superfluid flow and manipulate it from essentially the same approach, which is very promising. I wanted to get a better sense of what superfluids could be used for, because this is a new area for me. So I found this article called Superfluidity, What It Is and Why Does It Matter. So it looks like the direct uses of superfluids are pretty small in number at this point. However, it can be used, let's see, this one, it says, because of its extremely high thermal conductivity, the superfluid phase of helium-4 is an excellent coolant for high field magnets. While there are other unique indirect applications of superfluidity, they are most useful in the development of theory and understanding high temperature superconductivity. So they're mostly useful in terms of understanding what's going on with things like superconductivity. The original article I was looking at talks about this in terms of, they say scientists have previously created superfluids in liquids, solids, and gases, and hope harnessing superfluids properties could help lead to discoveries such as a superconductor that works at room temperature. So if you had some kind of superfluid and it has amazing heat transfer properties, then perhaps it could pull all the heat away from a conductive material and turn it into a superconductor. So a lot of the times superconductors, which is to say electronically conductive materials that have almost or virtually no electronic resistance, operate at very, very low temperatures. So the idea is that there's a logical connection between improving our understanding of superfluids, which will improve our ability to make superconductive electronics, and then that lets us make microchips even smaller and more powerful. So that's kind of, I would say, in looking at it, that's probably the main significance of this finding in terms of applications. Being able to measure and manipulate superfluids to a greater degree basically brings us closer to that promise of superconductivity. So the other article I want to talk about today is pretty weird. It says Earth and Venus grew up as rambunctious planets, and it's basically about the theory of planetary origin. And so there are models about solar system formation and then the formation of planets that astrophysicists argue about and try to tweak all the time. But planet formation, the process by which neat, round, distinct planets form from a roiling, swirling cloud of rugged asteroids and mini-planets, was likely even messier and more complicated than most scientists would care to admit. So their findings challenge the conventional view in which collisions between smaller building blocks cause them to stick together, and over time repeated collisions accrete to new material to the growing baby planet. So the conventional idea is you have a baby planet of some sort, a planetoid, and then asteroids and other planetoids are colliding with it, because that's just something that happens in the early phases of a solar system. And then when they hit, they basically fuse, and then you get a growing planetoid. These authors at the University of Arizona Lunar and Planetary Laboratory have a different scenario. Basically, they think that there were more hit and run scenarios than there were just, planetoids colliding and then joining. So they think that preplanetary bodies spent a good part of their journey through the inner solar system crashing into and ricocheting off each other before running into each other again at a later time. Because the idea is it's like a game of billiards. When the balls are really fast, they're going to hit and then bounce off each other. But when they start slowing down after a few hits, right? Because each hit, they're going to lose a lot of momentum. When they've slowed down a bit, they will be more likely to stick together next time, right? Like two very, very slow moving billiard balls, if they kind of hit into each other and then roll into each other. That's what they're picturing. So the idea is that if two planetoids collided, they won't actually combine on their first hit. Instead, what might happen is they might hit off each other, and then one goes over here and it ends up maybe combining with a different planetoid. Right, they say we find that most giant impacts, even relatively slow ones, and that's in quotes, slow, are hit and runs. That means that for two planets to merge, you usually first have to slow them down in a hit and run collision. One implication is that Venus and Earth would have had very different experiences in their growth as planets despite being immediate neighbors in the inner solar system. So they think that, generally speaking, material is going to come in from the outer solar system, and then it's going to come in and it's going to hit Earth, lose some momentum, slow down, and then go in and hit Venus. And that's going to be more common. And so one of the implications of that is they said that Venus will actually be compositionally probably have more material from outer solar system objects than actually Earth does. They say that Earth acts as a shield, providing a first stop against these impacting planets. More likely than not, a planet that bounces off of Earth is going to hit Venus and merge with it. And the reason it's going to bounce off Earth and then go to Venus instead of going out of the solar system towards Mars is that you can think of the sun as the center of a gravity well. And it's like, one way to think of it is like if you have a bed, we'll say, or a soft mattress material, and then you put a bowling ball in the center of the mattress, you'll notice that it will sink down, and that all around there will basically be like a sloping wall. And if you take a ball and put it at the edge of your mattress, you'll find it will roll down towards the center. So that's going to be the general direction. Things are mostly, if they're moving with respect to the sun, they're probably coming closer to the sun. So if something comes in from outside of the solar system, right, it's going to come into the Earth's gravitational region, it'll probably hit Earth, and then if it keeps on moving, it's going to move towards Venus, which is closer to the sun. One thing that doesn't make sense to me about this explanation is that based on this prediction, I would expect Venus to be larger than the Earth, but it's not. It's a little bit smaller. Anyway, I thought this was a pretty interesting article. I think that this is hard stuff to really know for sure. It's essentially forensics, but on a scale of multi-billions of years. And I just think anything could have happened. And it's probably hard to actually put together a real blow-by-blow description of what actually did happen. But maybe if we can get robots to Mars and take samples, maybe, for instance, we could test whether or not the rocks of Venus tend to be composed of material from outside of the solar system or farther out in the solar system compared to rocks in the Earth. So I don't really know if there's a way to distinguish that. Perhaps there's something related to the isotope composition or something along those lines. Well, thanks so much for watching. This has been another Science Update. I hope you will join me again in the future soon. Bye.